accelerating
on the road. So then you have the forward force is static friction, the backward is drag. How would the student know that?
Wait, is it not? So they have to.
We should linger over there. It sounded interesting.
So we've told them to ignore air resistance in every scenario.
Yes.
But in this scenario, they're not supposed to.
Okay, the second half of this lecture 12-13 coupling. And you need to go ahead and review a little bit of what we had there. And let me get that one set as a graphic. The thing I want to go ahead and just make sure you understand the little idiosyncrasies of the complex variable to field relationships, and we'll go through just the basic derivatives, integrals, and stuff real quickly. But then we'd like to take a look at the multipole structure of fields. And the dipole is the one that we looked at first. Well, we looked at monopole, and then I started to mention the dipole. So that's where we left off last time. But let me just go ahead and make sure that this item right here, the ability to invent source-free vector fields, that means also inventing inventing curvilinear coordinates. Now, at the end of this section here, this business with non-analytic source, the fields and the complex variables can be applied to that too. That's sort of a weird thing that I discovered as I was playing with this and trying to make it more useful. But we'll get to that at the very end. We've got a lot of things to look at that are interesting, and I also have to relate the fields that we're working with to some physics that they go with. It's pretty obvious that the fields that we made with the quadrupole is something that would be useful in electrostatics, or the monopole that we looked at can be either a magnetic field due to a wire, or we could talk about the monopole field. And well, let's go ahead and review this, and we'll get to that thing pretty quickly. But this idea of having the complex derivative, this derivative of a function with respect to z, and we're dealing with a complex function that has non-zero partial derivatives of the function with respect to both x and y. So we manipulate that into a form that has as its real part, first of all, we note that the real part of the actual function is the x component and the imaginary part is the y component. But then here what's happening is that the derivative has a real part and an imaginary part too, but this time the real part is half of the divergence of the field that this function is describing. And the imaginary part is the one-dimensional, you might say, curl, del cross f as opposed to del dot f, but only one component of it. So that's this particular structure there is a real number. And I'm going to be following along here on this screen, which is actually bigger and clearer. So maybe that's the one to focus on for some of this fine stuff. But the real crazy thing about all of this is that to invent a new source-free vector field, or to invent some really beautiful structures that have to do with the curvilinear coordinates that we're going to be dealing with in the rest of this mechanics class. The idea is that you simply pick any function that you can think of that you're, just have kind of like. Obviously the function that we took first was the field equal to z. Conjugate it, that is, change all the i's to minus I, make this f star function, and we've already shown that the z derivative of that is 0, identically. So that then gives us the what we call a divergence-free laminar field, but it's more than divergence-free, it's curl-free, and that's what the word laminar really refers to. So both the real and imaginary part, that is the whole function, has derivatives that would be 0 here in this, if we have followed this recipe with this given function. Now, the function that results from this is actually a quadrupole field, and that is shown, and we've worked on this one a number of times. I think I can pull up, let's see what's showing right now over here. Well, so we're talking about the monopole up here. Let's go to the this screen right here, where we're talking about the, let's see if I can make this thing, have to wake it up, I guess. Let me show it. Go ahead and plot this and get it active. The constant scalar potential of this field is made of these hyperbolas, and that you get by calculating the complex potential, and the complex potential, of course, is the integral of the field, and it's just a plain old calculus, one-dimensional calculus integral for having followed this recipe here. So these are the topography lines for the scalar potential, and then the vector potential arises as the imaginary part of that integral. And we plot that in blue as though it was water flowing, and of course the water is flowing in the direction of all of those arrows there, and hence this is often called the streaming or flux potential, this vector potential A. And remember, it's only a number here. It's not a three-component vector, which it would be in any book on electromagnetism that's talking about vector potential A as a companion, a relativistic companion actually, to the scalar potential. So that is all there is to the field, and it's a lot. You'd think that such a simple function of z, namely z itself, here was a constant a times z, and that constant can be complex. We'll show some examples of what the complex coefficients do. But for now, this is remarkable that just your first function you think of, which is just z itself, gives you something of this complexity. Now, I want to quickly compare it with what we're going to be talking about at the very end of this, and that's a non-analytic function. If I had not done this trick here of conjugating, if I'd simply plotted f of z, or if I'd gone ahead and plotted, say, the next one that we're going to be looking at, which is f of z's f of z equal to z squared, then you get something that's called the quadrupole at infinity. In other words, there's a quadrupole way out there somewhere, and this is we're inside that device that makes the field. That's the thing that's shown up there. Now, what we're going to compare that to is this guy right here. These two are both from z squared. But this one has not had that conjugation done yet. So this one is full of curl and full of divergence. There's stuff being created here, and there's stuff turning a rotor or something to make a circulation. For this one, that's not happening. And it seems kind of weird that you would say that there's no curl on this. It looks like if I make a loop here, that the integral around that loop of the projection of these vectors would not be zero, but it is. And this one is not zero. And also the flux through any closed thing, that isn't zero either. So this one has lots of divergence everywhere except at the origin, and lots of curl virtually everywhere, except possibly at the origin. So what I'd like to do at the very end is show how to handle that monster, that hurricane or thunderstorm or whatever in the lower right-hand corner. But in the meantime, let's finish the discussion of the functions that have had this recipe applied and which have everywhere on the plane that we're looking at a zero for curl and for divergence. So this is the one that we're talking about here. Okay, so the other thing that is true is if the field is a gradient like this, and that's the other thing that's amazing about this, is that you can write the field these two ways, but the idea of the having that divergence be zero or the curl zero, particularly if the curl is zero, then the possibility of having a potential arises. In fact, there must be a potential that has as its real and imaginary part, respectively, the scalar and the vector potential. So this was what we did here when we took the f of z and defined or sought, we're looking for a complex potential whose z derivative is that field. Then obviously, or sort of obviously, a simple integral of f with respect to z, which gives you z squared over 2, is the potential, which we were plotting there. And here's a complete plot, sort of like what we put on that screen 3 down there. So when you're reading the textbook, this is the 7th figure in figure 10 of unit 1. I always put the data associated with whatever we're plotting in a little white square off to the side of the figure. But the other thing that we need to talk about, besides the derivatives or the integrals of these fields, is what does that represent? And in the case of the thing here, we're thinking maybe of a force field, and then if you're integrating force with respect to z, particularly if you're integrating the projection of the vector associated with that, these little green arrows, dotted with a unit vector along the contour, that's the work integral, and giving you the work integral, then giving you the difference in potential between these two. And of course, that's the power of a potential, is it lets you avoid doing that integral if you have that function, if this field was completely integrable. So that's the deal. And then we can go ahead and rewrite this derivative of the potential here in terms of grad phi and curl phi. Here, thinking now of the real part is the x component of the grad. This part right here that's got an I in front of it, that just represents the y component, and that's a vector. That's another vector in the plane of the fields, field vectors. So remember that we don't have a minus sign when we're doing this particular type of mathematics, the complex variable view of the fields. Okay, now one other thing to remind that will not happen when we do the source non-zero fields is that these two results here are identical. Okay, so the gradient of the scalar potential is exactly equal to the curl of the vector potential. So you can do all of your work with just one of these or the other, or go ahead, and that's what this half and half business is. That since these are both contributing equal amounts, it doesn't matter. As long as these two numbers here add up to 1, you're going to get the same vector. So that half and half business is very great. Now, we went through what's analytic, what's not. If there are any questions about that, please raise them at this point. The circulation part, I also go through fairly rapidly here, and I'll do it on a clear screen so we can show. We have corrected that typography font issue, so make sure that that part of the lecture, that's it right there, is clear. And you see the trick is, once again, if the fields we're interested in are f star, and I want to do an integral of f of z with respect to z, well, I star twice in order to get the f of z, and then I do an integral with respect to z of that. That's this guy right here, which is this guy right here, and so forth, and I get a real and imaginary part that are, respectively, the ordinary contour integral, which is an integral that's a measure of how the force vectors are streaming, how closely they are streaming to the contour, that is, their scalar product with the differential r of the contour. And then the other guy right here, this one, after doing this is where the font issue came because of that not being kosher for the modern font system. Now it's right, and we just flip the zeros there, and then we're looking at a surface area that you imagine perpendicular to the curve, and we're asking how much f crosses that one. You see, so the streaming potential here, the delta A, the delta of that is given by that part. So that is interesting. Now, we looked at these things with 3D. I'll come back to that in a minute. So you can see, obviously, you can see here's a saddle. Here's the blue streamlines flowing from two sides to come out of the left and right side of the saddle. And this is from along the x-axis plus and minus, and this is along the y-axis plus and then minus out of the screen with the 3D drawing there. Okay, and let's see if there's anything else that I need to remind us of. Oh, here's the connection to the actual coordinate grid, if I've been very careful and marked off the topography lines with equal intervals of the coordinate, be it phi or a, And that means if I'm looking at the phi lines, then I would be incrementing this coordinate right here. If I'm looking at the A lines, the actual stream lines, those blue lines, then I'm incrementing the phi, right? Okay, so we make a Jacobian or Cajobian, whichever is more convenient, and make sure they're inverse of each other, which they are, and that's your metric for this. And I've got a couple of problems that make use of that, and then later on we're going to have lots of those kinds of problems. Now, because of the fact that the gradient of the scalar potential and the curl of the vector potential are the same, that makes the Jacobians very simple. It also makes each of these quantities, the function that describes the scalar potential and the function that describes the vector potential, they both satisfy this guy right here. And that equation is just partial of z times partial of z star, or the reverse. They commute with each other. So the Laplacian is just written as del star del. It would be one way to write it if the del was
Professor
two
Harter.
partial derivatives.
Excuse me, sorry, could
Yeah.
you back up 2 slides?
Yes.
Kind of a restatement, sort of a restatement question. So we see here that you can create these 2 fields are equivalent for the
Actually,
scalar potential or the
Yeah.
vector potential. So if
Yeah.
for an analytic function,
these two fields.
okay,
But they're not two fields. They're, in this case, equal.
the same because it's an
Yeah.
analytic function,
Yes,
which means we're in a source-free problem.
that's right.
So if we choose the proper boundary conditions, we can set up exactly the same force field.
Well, the force
Judicious
field,
choice of the boundary condition.
yeah, the force field, depending on what you're talking about, is, I mean, first of all, the force field is just a collection of arrows, those green arrows, right? And then the question is, I get tired of drawing arrows. I'd like to draw something simpler. The contours. First the red lines, okay, these guys, which we would later on call Q1, queer coordinate number 1. So those coordinate lines right there, okay, are all perpendicular. That is, they're the things for which the gradient of them is the green arrow at each point, right? And that had better be equal to, that is this quantity here, had better be equal to, because there are no sources of circulation, better be equal than flow, actually, no new flow being introduced, it better be equal to this. So, but this one is the curl, you see. This line, the value of this line at each point, right, is given by this crazy curl. The curl has only one component, namely the component associated with a direction out of the space perpendicular to it. Does that make sense? Anything else that you can
I
think of?
sort of thought it was interesting that you could, in essence, create the same experiment or system with either type of.
Yes.
That's
No.
why when
We're so used to just dealing with the scalar potential, but somebody else was just trained differently, a hydrodynamicist. Streamlining is the only thing they do, and they would say, what are you using that crazy feed function for? Right? Well, in the case of source-free things, they're both the same. They give both the same result. You can take the curl of the blue guys, or you can take the gradient of the red guys. You better get the same thing. And as a result, these turn out to be orthogonal everywhere. That doesn't happen with that one. Okay, so that one's the one that really comes up with queer coordinates. Okay, let's make sure that we understand the, I'm going to take this one forward here, to the monopole field, which we found was the one case, and that computer is really bad at handling black backgrounds, whereas this new one is not. So we've got to look at this one now.
Same projector too.
And it's the same make of projector. It might be, try switching. But in any case, this is a case where looks like this thing has divergence to spare, right? I mean, these arrows are diverging, are they not? But that's not the definition of the divergence. The question is, if I draw a circle or a rectangle or any sort of closed curve here and ask how much went in this side compared to what came out of this side, okay? And it looks like, oh, gee, there's little tiny arrows over here and there are really big ones here, right? But the thing is, these big ones are going through across less of a contour than these little guys up here are going through by proportion of distance, right? These arrows are down by, say, a half from these arrows, but then the length that they cross is half as big here as it is here. So when you add up the flux from across that one, these little guys over a big distance, it's exactly the same as the big arrows over a little distance. So no divergence anywhere on this plane except the singularity here, you see. There, when I draw a loop around there, I've got a heck of a flux coming, right? And that better be equal to the flux that I get out here, right? So just to remind you of your vector stuff, this complex way of looking at that vector field is pretty helpful. Now the curl is the same deal. When you draw the vortex field, the vortex field is nothing but I times this one. And you can see what the I did. The I rotates by 90 degrees, right? So I'll just take every single one of these vectors and rotate them in the same direction by 90 degrees. Bingo, vortex. Pretty cool, huh? So these are the two fields that are related to the ones I gave you a problem for, particularly this one. This one, you say, just like this one, it should be curl-free. This one's sort of obviously curl-free and not obviously divergence-free, but both of them are curl-free and divergence-free. This one is not obviously curl-free, but the same deal happens. You're asking if you draw, you know, a thing here and ask how many of these vectors are giving components along this contour compared to the ones here. It looks like they're really giving a lot of curl here and not so much here, but the same thing applies. These vectors right here, just like these, are twice as long as they are when they're twice as far away. So no curl anywhere except there. Okay, infinite curl right there. Now if I draw a contour anywhere here, I'm going to get that number. And I better get the same number by going on this big contour here, right? So this sort of unites the curl and divergence concepts rather coolly, you see. Now it's still only two-dimensional, but that's the dream of us, is to be able to take the quaternion and stuff and get us to all of this fancy mathematics can be done for three-dimensional, actually four-dimensional systems. But anyway, there's the difference between the two. Here the logarithm shows up right here in the real part for the scalar. Here an angle shows up for the scalar potential. Okay. And we're going to have the same deal here when we ask, you know, what's the curl, what's the complex derivative? It's the curl of the vector potential plus the gradient of the scalar potential. Each times a half. This is a half and half. It's going to work just as well as it did for that simple case where we had the z. This is this 1 over z. So much more spectacular. Okay, now curl-free is kind of what liquids like to do. And when the curl is non-existent, and I'm going to produce a curl, a high curl field in here. It's just like the one that's in a problem that's at the back end of the homework. I think it's the last problem. So I turn this thing over and go like this, get it stirred up in there, give some angular momentum, and produce a tornado, okay? But there's a shape, apart from the ripples of that thing that are propagating up from the nozzle, which is not perfect, apart from that, there's a curve. Okay, that's what I want you to derive, okay? Now the opposite of that curve is the curve that made my terrible failure here. My failure was I was thinking with epoxy I could make a really big telescope. Okay. First of all, I just wanted to make a nice mirror to show people real images in an optics class. And the little ones that they give you aren't very impressive, but a big one, oh, that'd be great, because you get in there and you could poke people's eyes and do all kinds of things. You know, a figure comes out of the mirror, right? You've seen real images, right? They're really spectacular. Unfortunately, the epoxy gets warm and distorts, and so no chance of getting an optically perfect curve here. Okay. R.W. Words in Canada actually built a telescope. It was almost as big as this room on a rotating thing. This is what you get when you put epoxy on a record player that's going at 45. I'm sorry, 78. I made it go as fast as it would go, okay, and then hope for the best. So there's use for this, but it's not optical, okay. It's a neat way to show some things we'll show later on in mechanics. But anyway, I want you to derive that curve as well. And this is one where the curl is constant, okay. Now this connects with the sophomore physics survey. I'm asking you in a problem to write a little essay on that, a couple of sentences. Okay. So anyway, those are the two archetypes of, this one is very definitely curl-free, and therefore it's part of the conversation for the source-free fields. This one's got constant source everywhere. Rotation is going on everywhere, and the curl is constant, but not zero everywhere. Okay, now, going forward here, we mentioned that the thing that's different about this particular power of z, namely -1, is that its integral is not a simple power of z. It's this darn logarithm. And that's what makes the complex variables both vexing at first, but then extremely useful. And the whole idea of that is has to do with the fact that you pick up 2 pi every time you go around this thing, and that's for the constant equal to 1. Make the constant anything else, and it's 2 pi times that constant a. So we're just imagining going up a helicoid here each time we go around. And that was what we were showing on the other screen here. That's what we calculated last time. So I'll flip that up here just to remind you of that. This is the 3D view of a particular constant phi line. And you see that what I'm doing every time I cross, I come up with a helix to that point, and then I just have to drop back by 2 pi to continue. Otherwise, I just keep adding 2 pi as I climb the, well, I guess you could describe this as a lighthouse staircase, right? Or a prayer tower, if you're going back to Arabia, lots of prayer towers. They've got helical stairways inside of every one that I've seen. Okay, so I'll pop back to the text here and point out that when you multiply 1 over z by I, you get the vortex. When you leave it alone, you get the flux nozzle. This one right here, and that's obviously got a problem because of the blacking out of this particular computer. We'll go ahead and use this one right here. Here you can actually see that you have streamlines that make a spiral that goes in the opposite direction of the flux. I'm sorry, the flux lines, the streamlines, make a spiral, a logarithmic spiral, because that's what this function is, logarithm of the dependent variable. Here, the red one just matches. They're both arrows that have been rotated by 45 degrees everywhere. And these arrows are following the blue lines. These arrows are perpendicular to the flux lines, you see. So are these. The flux lines don't show up as well, but you can see them there a little bit. Change this to something like 18 degrees, and you get a sort of a flat spiral, very kinky spiral when it finally starts curving in here, and then a fairly flat one is perpendicular to it. So I ask you to go ahead and work out a couple of examples of that on the problem set. And we're at the place where we use that. The people that are doing galaxy, they've got thousands of galaxies that they're looking at. Some of them are looking at them for the first time, but most of them are out of an atlas or a computer storage of things that, I mean, there's a very large thing there. Our galaxy is not quite as spectacular in terms of having arms like that, but it's sort of a similar object. Okay, now, the idea of getting higher multiples is totally connected to taking a derivative. And this time, you guessed it, a z derivative of a monopole will give you a dipole. But at first, you have to see what a physical dipole is. These are mathematical dipoles here made at an infinitesimal limit. This physical dipole here, you see, has a distance between the two charges, positive charge here, making a tower, a negative charge, if you're thinking of electrostatics, making a very deep exponential approaching valley, and then kind of a steep but still not infinitely steep slope coming up the fall line right here. And you imagine this is a positive charge letting the water all flow out, but I'm talking about electric field now, flux, flowing down, 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 down to go and end up in the drain here, which represents a negative charge. Okay, this is Faraday's dream, so to speak, is to have a quantification of that sort of notion, that something's flowing in the electric field direction. But the slope here is not infinite. For this, for the thing that we're going to be making, this is just a plain old dipole located at A, Z plus this distance over 2. The other one's located at Z minus that distance over 2. And you put those two together and you get a quadratic function in the denominator that pretty much describes a physical dipole. It has a finite plus minus separation. Okay, and it would be just the sum of the logarithm for each of those 2 points. The z plus delta and the z minus delta over 2 gives you that logarithmic function for the potential. But what we're interested in is what does that become? as you let delta get smaller and smaller and smaller. Okay? So what happens when you talk about this, and what you're ending up with here is the best way to get the next highest multipole is to take a derivative. It's basically a copy of the monopole, and then another copy with the sign changed, summed up and divided by the distance between them. So we do it balanced right here, delta plus over 2 and delta minus over 2, and let that delta approach 0. So that's what we're talking about when we talk about the next thing that comes up after a one pole is the derivative here. This is the derivative of the potential giving the force for a one pole, and the phi for a one pole is the logarithm we were just talking about. And now we're going to, if you're thinking about electrostatics, we're going to let the charges get closer. If you're thinking about magnetism, if these are magnetic fields, you're thinking of two line sources, equal but opposite source constants, that's current going this way and then current going the other way. Then this is what we're taking the limit of right here, and that is the field of a two-pole. What's that called? Well, that's a quadrupole. And the idea of that being simply that, let's see if I've got this here, it's either the derivative, this force here is either the derivative of the monopole field, or it's the second derivative of the scalar potential of the quadrupole. So there's the scalar potential of the quadrupole that's going to come out of having a quadrupole field. Okay. So this is another way to state it. By taking that derivative of either the potential or the field, this derivative, or this derivative, you get the next higher multiple field. Okay, so here to compare with the one that, and I hope I can show it better there. That you can at least see what we were looking at just a minute ago with finite delta. You see that you have a straight line up here. This has infinite slope everywhere, right at the z-axis, if you will, or the phi axis is what it really is. Okay. Now, all of these things are really beautiful if you look at them in 3D, and I've already told you that these are in the textbook available to be looked at by just putting your face against the thing and then pulling away slowly and hoping your eyes, you can control them to keep looking in the same direction. Okay, so that's what we're talking about when we say a quadrupole. A quadrupole at origin. We've got let's see, we've got the one pole, and then I'm sorry, this is a dipole, a two pole. Okay, the quadrupole's next. We're going to take a derivative again to get that. Okay, then here's what it looks like. Okay, and what's interesting about this one, this is kind of neat. If you draw the streamlines for this dipole, okay, if you plot the first the equipotentials and then the streamline, they're all circles. This does not happen in 3 dimensions, but in 2 dimensions. This is Thales' dream. Okay, there's a Thales circle right there, right? So we're talking about r here, the radius here, being the distance. That's this distance right here. That's a over the vector potential. This one is a distance over the scalar potential. Both the vector potential and scalar function have the same numerical value here. The circles are the same size. But the r value to that contour, or to this contour right here, okay, is given by either the cosine or the sine. in this case the cosine of the coefficient of this thing, which is set to 1 for purposes here, 1 over the scalar potential times cosine, or this one, which is the scale. This distance right here, that's got the scalar potential in mind. This one right here, this distance right here to this circle is the sine. So that's really some very simple functions, and this is a summary of it right here for the mathematical dipole, perfect dipole, where these charges have been put so that they're less than a pixel separating them. And this is what you would see as the field. Okay. All right. Next is the quadrupole. That is, if you have a force field for a dipole, take a derivative of that, and you get the next stop here. And remember what taking a derivative amounts to. What taking a derivative amounts to is you take one thing with a plus sign and the other thing with a minus sign and put them close together. So right now we've got a dipole with a plus sign and then a dipole with a minus sign. Now the dipole, of course, should, I don't know how to do this without making an obscene symbol, right? But let's do it this way, okay, and I'll just do this right here, okay, and putting those two guys close together, okay, making, well, count them, they're 4 poles, a quadrupole. And each time you do this derivative, you're taking another pair, so next stop is octupole, 2 to the 3rd power, and so forth, okay. Now, all of this is being done in a line. It doesn't have to be. There's all sorts of freedom as you start to go to the higher multiples of how you arrange these. And when you then allow it to happen in 3 dimensions, it becomes quite complicated. That's when group theory takes over and really makes what is promising to be a mess into something really beautiful. But this is a good start right here for that. And what you're seeing for this field right here, which is what has a field of 1 over z cubed, okay, a potential of 1 over z squared. That's the phi function. There's the f function right there. And the quadrupole at 0, that's, let's see if I've got that. What I'd like you to compare in just a minute here is the quadrupole where the charges are at home, and then another one which is on this far screen there, which is a quadrupole at infinity. Okay, and I'm going to try to make some sense out of that. What sounds like useless garbage, but it's a really powerful way to look at this. So here's where we begin to ask the question of, what happens when you have, first of all, a monopole, and here we're looking at the force field, and right next to it the potential. Okay, that's already a -1 power. All of these down here are just powers of z, and we've looked at a force field that had just one charge at infinity, okay? And then this one has a 2 to the 2 pole. This is a single pole at infinity. This is a 2 to the 2 pole at z equal infinity, 2 to the 3 pole, 2 to the 4 pole. And you can kind of see how that's showing up with the field equal to z squared. We already looked at z here, which gave us a quadrupole field, something that came in from top and bottom and went out, say, x plus and x minus. This one, you see, you're going to go in basically 3 directions, and it makes a hexagonal shape to it, as you can see by looking at that drawing at the far screen. So we've just done a dipole here. First we did the monopole, then took a derivative of this field here. So this is a dipole at origin. This is a quadrupole at origin. So it's the origin versus infinity game that we're playing here, if we're thinking of these things physically. Now, speaking of physically, let me pause for a minute and say what would we, what would this describe? I already said electrostatics and magnetostatics is a pretty obvious for us, but for somebody that's just off the street, if you're going to tell them what are we doing here, well, we're describing surfaces. We're describing the form of surfaces that you get if you have a great big soap film on a ring. Imagine a sort of a trampoline-like thing with a soap film, okay? And I poke one place there. I make a curve that is really close to the monopole. It's really got that, if you look at it this way, exponential shape, or look at it horizontally, logarithm is what we calculated, right? And if you poked it two places, okay, like that, and you didn't pop the bubble. That's the catch. You see, is you have to use some really amazing soap films in order to pull this off, and you have to do it with something that's not going to pierce the thing and cause it to just contract it to a bubble, to a drop. But this is actually quite doable with some of the soap films that have really high polymer content. I have had some luck playing with it, but not enough to actually bring it and do it here right now. But that's kind of one thing that this is describing. These are all minimal surfaces that you're making, because it's relaxing to this lowest energy. Okay, so that's one thing. But the other thing is just flow of something. Well, whatever electromagnetism, that's the flow that Faraday conceived of. But if you're talking about temperature, heat, the flow of just plain thermodynamical energy, these functions are all at your disposal for a two-dimensional system. So that's I'm just trying to sell this stuff that it really is. There's so many different applications to it, and I'm talking about just the two-dimensional stuff. So the idea of making this to higher dimensions is sort of a driving an impetus for thinking about this and then trying to generalize it. Okay, now the real thing here is that all of the field terms, except the one pole, okay, have a potential term that is a power. So the only place that you see a logarithm here is the potential associated with this one, right? So this is a weirdo, okay? Put it in red. It's different, really different, in the sense that it's not a polynomial. I mean, it's not a monomial. It's not a z to a power. It's the only one. But that makes for some interesting discussion. And if we want to think about a mapping between z and 1 over z, that's what I call a w, okay? We can imagine replacing the z with that. In other words, let z be w to the minus 1. That means w is z to the minus 1. So we have two equivalent spaces, one at infinity and one at 0. Now, how do you arrange that? How do you, fix it so you can have a map? And once you've done that, then you can make connection between a dipole at origin here and a dipole at infinity. You see, you can make a connection between these objects, a quadrupole at 0, a quadrupole at infinity. Just by saying, well, this is W right here. Okay, this is over here is W squared, but this guy right here is Z squared. So, question is, what is it that you're actually looking at? And this is an attempt to show that. This is the once again Thales' construction. Okay, gives you the stereographic transform from stuff that's inside the unit circle to, and I'm just taking a z here, z equal x plus iy here, to a point w, which is 1 over z, and is outside of the unit circle. So something that's a half here is going to be out at 2 units here, and so forth. As we approach the top here, you see, as I bring the thing closer and closer to the origin, this one goes marching ever closer to infinity. Now the idea of the circle here is to have a Thales rectangle inside there. I haven't seen any descriptions in math books that use this to point this out, but then I guess they don't want to go back 600 years, more than 600. 600 plus 2,000 years. So right there is a nice right angle. That's this right angle here. That comes off of the two sides of a Thales rectangle. So it makes a very clear thing. And then it shows that you're dealing with an angle over 2 when you measure elevations for this thing. So here is once again that list of monopole, dipole, quadrupole, okay? And for example, a monopole field at the North Pole, that's this guy right here, is a monopole field at the South Pole with a different sign. This monopole up here, say, is one that's putting stuff out. That's a positive monopole. There better be a negative monopole waiting at the North Pole to take it all back in again. But when you come to talk about a dipole centered at the North Pole, okay, that's what we call z equals 0. Well, over there at z equal infinity, which is w equals 0, we will have a uniform field, w. That's what you get if you take one of these programs and just go for the no pole. Well, it's a constant field there. Phi equal to w gives that. And so forth. Each of these things gives something that's associated with it on the other side of this globe. Now, this other thing that I mentioned here is that this guy right here is the only one, the only power of z for which a contour integral, okay, is anything but 0. Okay? Z to the minus 1. That's the one that has a non-zero value for the contour. Okay? What mathematicians call a residue. All the others don't have residue. So this formula for the non-zero contour integral associated with f of z being z to the minus 1 power is just the first in coefficients of a Lorentz series. Lorentz series is a Maclaurin series that has a back end that has powers that are negative values as well as positive. So what we're looking at here are coefficients that will just be, first of all, the one that isn't a residue, but then there'll be numbers associated with f of z, assuming that's an analytic function, over z, or that's going to be the a0, then a1 will be this over z squared. So we're talking about here a monopole field here we're talking derivative of monopoles dipole field at origin. And then these other guys I'll be working with power series. Well, they're at origin of W space. So the as I say, this is a source analysis where we're counting all of the monopoles at once as a description of a function. So the idea is that these loop integrals, they hold for any loop about a particular origin. This is z minus a now, not just z minus 0. So put your monopoles wherever you want to make some function that's a combination of these things. And an integral like this is, first of all, this thing is given by 2 pi times the value of that function at either 0 if we're talking about the simple 1 over z, or 1 over z minus a is the function at the value a. And as long as the contour doesn't touch a, this integral will give the same value for any contour that surrounds that point a. And that's very useful. This is called Cauchy's integral. And then what you do is you say, okay, I've got a function of a, let's take a derivative with respect to a, and get the next one, and so forth. And these are the coefficients. These are the coefficients of the Lorentz series. So this is how you would take a pathological function that has singularities in various places. And just by being able to write the function that way is kind of neat. Anyway, that's the basic idea of this complex variables using functions that are analytic. It means only function of z. Now, we mentioned also before, I'm going to go through this very quickly, but you should also take a look at, if you get a chance, the effects of mapping. And I've given you a problem that has essentially that. The basic idea of mapping from the z space to w space, where the function that does the mapping is any one of these functions that we've talked about, not just the 1 over z mapping. So here w refers to in general for a given z function. And this program allows you to actually do those mappings in you can actually draw the 2 coordinates and then draw curves in one of them and see how they come out in the other. But the important result here is that our Jacobian is a rotation matrix. And then it has an extra term that is the determinant of the Jacobian. So it's almost a rotation matrix, but it may be scaling as well as rotating. So the examples I've given you for homework, here's w equals z squared. This is the inverse of that. So we're going to be making use of those coordinates for things in mechanics. So it's worthwhile getting them as much under control now as opposed to later on. Okay. Now, we've only got a few minutes to do this, and so I've compressed it somewhat. Instead of having a step-by-step slide here, I'm just laying it out. What we're doing here are talking about analytic functions generalized. So, and this is just an excerpt from the very end of the chapter 10 of the review, and another book called Analytic, which is describes the program that we hope to get in HTML pretty soon. Anyway, the potential field function, or the force field function, or the source function are all important now. Before, we didn't have this, but now we're going to have it. We're going to have a phi that's a function of z and z star. And of course, that will mean two parts, a scalar potential and a vector potential of x and y being related to z and z star, as we've done numerous times here in that expansion there. So instead of having just these two, we're going to have a third. So we're going to be having some sort of density that's making stuff be created, and then something that's mixing it up, curling it up, something that's more like a current than a charge, if you were thinking in terms of electrostatics. So the source definitions that we used before, when there was no source, that is a source-free analytic description we've been just talking about for the last couple of talks here, where the derivative of the function of z star was 0. That's what we did was we made our function of z into the function of z stars by conjugating it. We could go on the other way. We could have used z as the variable we wanted to make sure that let z star be the variable. Same thing would happen, just not quite in a nice form that we got. But in any case, the idea is that the derivative of the thing has this divergence and curl as a real and imaginary part. Well, we're going to have something different now. And the way we're going to define it is, first of all, I'm going to take that 1/2 out and put it right here upside down, that is as a 2. So you put a 2 times the derivatives either of f star with respect to z, and f star, remember, is a function of z and z star, so this is not going to be 0, and this isn't going to be either, so that's sort of the conjugate of each other. And then we're going to have a relationship between a scalar potential, that's this guy here, but it's going to give us the entire force field. It's just that the gradient of phi is not going to be equal to the curl of the A. So we're going to have a phi and an A, but they're not going to behave like they did before. Okay? The idea now is that the source will be the derivative of the field. That's the new relationship here. This isn't going to be 0 anymore. It's going to be this. So we make that happen by just writing it down. But the basic idea, of course, is that the real part here will be the divergence of this vector field that we're going to produce, and this will be the curl. So we're really going to be separating a field into one that can be described by Poisson's scalar source equation. Meanwhile, the imaginary part, the Biot-Savart type stuff, the vector source stuff that you have in magnetism, magnetostatics, is also going to be described, but these are not equal. Okay, these are the two things that turned out to be equal as far as a divergence of the field and the curl of the field. Okay. Now, the real and imaginary parts play the same game with all of this stuff, so that it looks like this, and you end up here with this thing, which is going to be have a real and imaginary part that are the vector components. It's going to be a gradient with 2 components. This is going to be a curl with 2 components, and these are going to be the things that describe that. This will be the x component. This will be the y component of this one. This will be the x, and that will be the y component of this one. So what we're going to do is get a longitudinal field that is given by a gradient of a scalar on top of a transverse field that's given by a curl of the vector potential. Tall order. I didn't think it was possible. But I should point out, this is a case where the potential force and source field equations are essentially analogous to position, velocity, and acceleration of mechanics, Newton's equations, Newton's calculus, right? So generally we talk about starting with an acceleration, okay, and and then integrating that acceleration to get a velocity. And then we take the velocity, integrate that to get a position, right? And then a double derivative of that position gives us the acceleration. Okay. So when I go this way, I integrate. When I go this way, I differentiate. You say. Okay, and I can, I come to this point right here where I have a second order differential describing the relationship between this and this. Well, that's what's going to happen here. There's a Laplacian-like equation right there. Then there are the various equations that I've kind of just written down before. Okay, let's take an example. That's the thunderstorm at the lower right-hand corner of that. I'm going to say that I'm going to start off here with a function of z, as z star squared, or I can start with f star z equal to plain z squared. Here I get a source function, not 0 this time, because I picked something that was a function of z all by itself, just plain that. So that's my derivative for x plus for y. And I have, as a result of this, a 4x for the density and a minus 4y for the current, or whatever you want to call this this particular source. And then the scalar potential that goes with this, that's the integral of the f of z. That's this thing. It's kind of weird now because you integrate z star squared with respect to z, you just get z times z squared over 2. That's this guy right here. Let's see if I've got that right. Anyway, that comes out to something that has a real and imaginary part scalar and vector potentials that look like that. And result then is that the gradient of this scalar gives me this, this, and this. What I want to do is show what those things actually look like. I'm going to jump ahead here to that part right there. There's what the two scalar potential and the vector potential look like that. And there are the vectors that go with them. In this case, scalar potential gradient of it gives me the longitudinal field. That's this F sub L right there. And the other one gives me the transverse field. The transfers to this field roughly. But then combine those two. Okay, put them on top of each other. Here's the scalar potential here, not orthogonal to the vector potential. And there are the vectors that come out of each one of them being added up. And that produces, the sums of that is the field that is the thunderstorm there, that z star squared gives, or z squared gives. It's that field right there. So we're just looking at the actual sum field right there. It doesn't look so much like a thunderstorm when you put them with lots of spacing between them, but that's what you're really dealing with, is that there. So this is a description. These scalar guys go in here everywhere, and these guys go everywhere there to make this thing, which has curl everywhere and divergence everywhere. Okay, so that's something you don't have to worry about, because I'm not going to do much with it in this class, but there's other stuff coming, I hope, that connects to that, like the understanding the Rinaldi way of doing electromagnetism, which is still a puzzle to me, and also a puzzle to Rinaldi because he hasn't really made it completely work yet. But these are just some things. This is extra stuff. This is stuff that's outside of the main line, and it's just it's up to you whether you do anything with it. Okay, so that is it for today. We're going to be going into the mechanics of the trebuchet in the next couple of lectures, which will develop mechanics once again, but now showing you what it works like when the variables are quite not so well behaved.